Okay, there we go. All right, folks, we had a little technical difficulty there to start off, but machine learning primer, what is possible today? The briefing room with yours truly, Eric Kavanaugh of the Bloor Group and Perforce. Yes, indeed. So here's a slide about our clients. Big thanks to all these folks for celebrating 10 years at the Bloor Group. 10 years we've been going strong. So big thanks to all these folks. The topic for today really culminates a lot of what we learn about. So we're talking about machine learning and what you can do with this technology today. Here are some of the big players in that space. Amazon, of course, Microsoft, Google, IBM, those four biggies. Well, they want you to do the machine learning in their environments. But I actually see a bit of a pendulum swing back to on-prem for this particular use case, because I think what you're doing with machine learning is going to be highly sensitive. It is your intellectual property. You're going to want to protect that. And I've seen some interesting developments just in the recent past about how companies are able to use their own data centers for this kind of machine learning. In fact, it's a company I ran across at an event in Denver, the Teradata conference, that basically allows you to refactor your existing servers to look just like Amazon S3. That way you can port from Amazon right over to your environment and you're off to the races. I see that as a trend coming forward. I wanted to show you machine learning in practice. Things are happening right now today that are allowing you to use machine learning. So this is just a screenshot of my Gmail from earlier today, and on the right-hand side, you can see where it says, hey, I typed hey, and then in gray, it's Bidwell. They call this, and what is it called? Smart Composer or something like that, smart composing, where basically Google, and this is if you use the Gmail client, is presuming it knows what you want to say. And what's kind of interesting is a lot of times it's right. So here is, as I started writing some text in this email, hey, Bidwell, are you coming to the show? T.O., it said, oh, tomorrow? Well, actually, I meant today, but it said tomorrow, and it's interesting that it figures out what I'm trying to accomplish. So this is really, really amazing stuff, folks, and it's changing what's happening in the world right now around us. So machine learning is not just far off in the future, it's happening today. So here's one of my favorite concepts. What is the most important aspect of any work environment? Morale. And I think the narrative is dead wrong around machine learning and artificial intelligence. They say it's going to take away jobs, it's the red-eyed robot, all that nonsense. In reality, machine learning is going to tackle all the really boring, tedious stuff that we don't want to do. And it's going to let us do the fun stuff that we really want to do, like hang out with our kids who just showed up. So let's move on. This is one of my big predictions that in the future, and it's happening already, in fact, laws are going to be adjudicated by artificial intelligence. So we're going to have these technologies actually cranking through really boring stuff like adjudication. You'll be able to figure out on your cell phone if you want to accept a penalty and a fine and probation or whatever. Instead of having to go down to the courthouse, it's going to go through your mobile phone, and the AI is going to be in the background taking care of that stuff. So these are just a few examples of what's going on. This is not about me, but the important person on this webcast is Justin Rioch of Perforce. And Justin, I'm giving you the keys to the WebEx right now. Take it away.
Thanks, Eric. How are we looking? Can you see my screen?
You look good.
Fantastic. So for those of you who haven't heard one of the episodes that we've done in the past, Eric and I have done a number of these webinars and interviews now at this point, kind of talking about trends and things that we see and concepts around free and open source software. So thanks, Eric, for another opportunity to talk at some people today about really one of the most, I think, interesting and certainly powerful subjects that we're seeing in the industry today, and that's AI and really machine learning. The type of AI that we're talking about today is machine learning. So I'm the chief architect for a division of a company called Perforce called OpenLogic. It's very confusing. We were just recently purchased by Perforce, and previously were owned by a company called Rogue Wave, who in turn acquired us about 6 years ago. And the purpose of our team and company is really to help enterprises comfortably and safely adopt open source software. And so we get to see a lot of interesting use cases for free software, and I've certainly seen some interesting things happen in the industry around some of the open source frameworks that assist in helping developers build machine learning models. And so we're going to talk a little bit about that. And And Eric, just kind of stop me at any point for questions or discussion, or if you really want me to hammer on something. But we're just going to go through this presentation that I have around some of the real world use cases for AI and ML.
Cool beans.
All right. So let's do a quick recap of neural networks. Again, this is not, a real focus on how we build neural networks, but I do want to make sure that we're all kind of level set on the terminology and the concepts. This may be a refresher for some people. It might be brand new information for others, but hopefully we'll just kind of whip through it and we won't go too super deep, but I think you'll have enough of an understanding of these things to really kind of keep up with the rest of the presentation. So again, really more about real world application of deep learning, but let's refresh a little bit. So first of all, can we all agree that deep neural networks are not sentient robots that are going to destroy humanity? At least not right in their current state. And when we learn about it, when we actually see what's happening, you'll see that it's not actually that smart. When you pull the math apart, it's linear algebra. It's math that's repeated lots and lots and lots and lots and lots of times, which would make it very hard to do by hand. But beyond that, it's kind of brute force in the way that the quote kind of magic behind it works. And so we're going to look at that. And so really then the too long didn't read version of all of this is that they're just complicated statistical linear algebra equations, and they're repeated lots and lots of times. And hopefully each time we repeat and run random data through the thing, we get a little bit more accurate. Fraction more accurate. And if we get a little bit more accurate, we remember what we changed about the network to make it a little bit more accurate. And we retain that, we reuse it, we test it, and we become more and more accurate. So what we end up with then is this mathematical mechanism that's really just good at recognizing patterns in data, which would be hard for us to discern or kind of see with the, as humans with just our regular eyes or our ability to do math by hand. Apologies, by the way, for the cat in the background. That is my cat, October. He has been on other webinars and presentations in the past. He is a 15-year-old, sweet but stone deaf cat who doesn't understand how loud he is. So he is fine. He doesn't need to be fed or anything. I've had people actually write questions and stuff. And is your cat okay? Do you need to go check on the cat? So just to put everybody at ease, the cat's fine. He's just loud. That's October.
I love it.
So anyway, so back to this. What do we end up with? We end up with these math equations that are just good at recognizing patterns in data, right? Patterns that might be hard. Although we may see these patterns, our brains see these patterns very easily. To try to represent these patterns or to find these patterns by sifting through lots of data would be very hard for a human being to do. Tedious, I should say, not hard, just a lot of work. But we're already interacting with these trained neural networks or robots. We can call them robots if you want to, all the time already. You're already surrounded by this stuff. When you use your phone's GPS, it's not a human being who's like reading an atlas and planning out a route for you in seconds. That's machine learned, artificially intelligent robot running in the background. It's software that's taking a lot of input data and saying, all right, the output of what I'm going to run through is a good route for you to get home and avoid traffic and all that stuff. When you scroll through your news feed, it's not like somebody at Facebook is saying, oh, I'm going to hand curate these articles for Eric every, hour and send them to his news feed because I know just the kind of stuff that he likes. No, it's a human, it's a non-human, artificially intelligent robot software that has been trained on your likes and your behaviors and is feeding you relatively accurate headlines that it thinks you're going to enjoy. When you take photos with your newer, Android phones like Pixels or whatever, Google in the background loves to generate these stylized photos for you or to create albums, and it does that by recognizing people's faces in the photos using neural networks, using trained neural networks, and grouping the photos together. It's really just a simple data categorization or taxonomy problem. So you're seeing it everywhere already, and they're enriching our lives. And they work best when we don't really have to think about them. So to Eric's point, these tasks that we're doing with these things, they're menial tasks because machine learning, although it is powerful, it's not that powerful. We'll see. It's got a lot of limits still, which we'll overcome. But right now, in its current state, all it's really good at is doing things like classifying photos or recognizing objects or, reading handwritten data, and getting, more sophisticated, like helping us with logistical problems. But again, like Eric said before, I love that he kind of brought that up. It's just stuff that we wouldn't want to do by hand. So again, going back to what these are. So deep neural networks, where do we see them? What are they doing? What are they not? What are they? What are they made of? Well, when we say that something is a neural network, it really is a mathematical reconstruction, a highly simplified mathematical reconstruction of our own brains as neural structure. So there's no question about that one. We took, a nod from the way that brains work and the way that brains learn, and we tried to just virtualize that, if you will, using math. Our real brains are comprised of these neurons, which are kind of these semi-binary cells, and they can output electrically and chemically a certain state based on an input or maybe a set of inputs. And then we chain these neurons together, and so those neurons can then provide output that becomes input to another neuron, or maybe you can take the output from some other neuron and provide output based on that. But where things really get interesting is that the connections between these neurons strengthen and weaken depending on how often they're utilized. So how many times do we utilize a neural set in our brain that allows us to recognize the color blue, or more importantly, the difference between the color blue and the color yellow, right? How many times do we focus on that and use that area of our brain and learn effectively creating new neural pathways just by utilization of those neurons? How often do we go through those physical activities? Because when we do that, when we utilize those neurons, the neurons change, and that means that they change their output. But we retain the structure. We retain those strengths and weaknesses within the fabric, within the neural fabric. And that's how effectively, that's a very simplified view of how we learn. So when we create an artificial neural network, we just try to recreate that same structure using linear algebra. And the base unit, the most atomic unit then of this, is called a neuron. And that's just an algebra function called an activation function that returns some kind of state. A lot of times we see this as either a 0 or a 1. And the purpose of this really is for us to be able to feed some data in, and then with some associated what we call weights and biases that's put in with that data, which you can kind of liken to that strengthening or weakening of a single neuron. We provide that in, and then some kind of output is provided. We then chain all of these. So when we put an input and output layer in front of this activation function, so when we give that activation function the ability to take data in or push data out, we now have what we call a node. And then we chain lots of nodes together to form a layer. Again, this is all math, and this chaining is done by the output of one linear algebra function forming as the input for another linear algebra function, right? So we're chaining functions together, and we're doing it really at a massive scale. We're doing it across matrices. These matrices form layers, but again, it's really just all statistical math. There's just a lot of it. But then at its simplest form, what we would call a neural network, we have what we call an input layer, which is where we're going to be providing input, like actual input, maybe pictures of license plates, or when you do those CAPTCHA images, when those annoying CAPTCHA images when a site wants to verify that you're human and you have to go click everything that's a traffic sign, what you're doing is providing training data that says, okay, if I take this picture of this stop sign, is this a stop sign or not? That was what the output layer tries to do. And so the magic then of this deep learning really lies in these hidden layers, these layers in between the input and the output layer that act a lot like sieves. It's the best way I can think to explain the way that the math works in each of these layers. So if you think about it like when you're searching for stuff in the sand, you might use a sieve to do that, and the purpose is to shake out all the useless sand and just find the objects that you're really interested in. The sieves can kind of work that way, except based on the weights and biases that we apply to these layers, we kind of change the shape and size of the holes in the sieve in this metaphor. And then so we shake different stuff out of the sand based on that. And as we get closer and closer to what we want to shake out of that sand, we remember the size and shape of those sieves along the way. And that's really almost like a sort of a physical metaphor for how we would train a neural network. We provide random weights and retain biases, and when the output layer is close to what we think it should be based on our trained data, we sort of reward the algorithm and say, okay, retain that weight and let's try it again. We do this hundreds and hundreds of thousands of times. And by the time we're done, we have a series of these mathematical layers that if we pass in some arbitrary form of input, its output will be a pretty accurate predicted model for what we want out of that input. So it's very brute force. We don't actually, it's very random. It's based on large sets of random and hopefully very varied data. So it just helps our networks find these patterns more easily. But it's just a brute force of pushing random stuff through, retaining what works and throwing away what doesn't. So as we pass sand through these sieves, then certain objects don't fit, and then this pattern recognition really just happens mathematically. By passing these random weights and biases in and then comparing the output layer to the real world data that we have, the training data, we can see how distant that random data is. And so we reduce then the cost of training. Again, this really is a mathematical representation of what happens when our neurons get stronger or weaker and then change the output that happens in our brain. It really kind of the same thing happening mathematically. So, you know, it may take a minute to wrap your head around. Some people prefer a picture. I know I always prefer a picture. This is a very simple neural network with just one hidden layer. So you can see on the left, this layer 1 is our input. So this might be a mathematical representation of a picture, or maybe a handwritten number that we want to try to decipher and figure out which real number it is, right? But all the stuff that you see on layer 1 is going to be our input. Then we're going to pass through these sieves, right? These mathematical sieves, these hidden layers. And this is the real challenge to AI and ML developers, is to structure these hidden layers, and also in many ways to structure the behavior of the network itself. This is really a very simple one type of neural network. There's lots and lots of different types of neural networks. But the challenge to real AI and ML developers is to pick the right neural network for the task and to design these hidden layers, the shape and size of these hidden layers, to really fit the problem that they're trying to solve. And there's all types of further approaches where, you know, right now we're just talking about supervised training, but there's unsupervised training, there's adversarial training, there's all these different ways. So again, we don't want to go too deep down the rabbit hole. Just know at this point that what you're looking at here has an input layer, it has one hidden layer, this middle layer, this sieve, and then it has an output layer that's going to give us our result. So when we have a neural network that has a lot of hidden layers in between, we call that a deep neural network. And when we're using deep neural networks for the purpose of machine learning, we call that deep learning, right? So when you hear deep learning, that just means we're doing machine learning with deep neural networks. And what does that mean? We're using neural networks that have a lot of hidden layers. And those hidden layers are what let us suss out these complicated problems, or excuse me, complicated patterns in these data sets. So that's really as far as I want to go here. But, you know, entire college courses are offered on the subjects, and really we have just barely scraped the surface. But you do know enough, hopefully, at this point, I think, to kind of keep up with what we're going to talk about with some of these real-world examples that we've seen with actual businesses making use of deep learning to improve their efficiency. We'll talk about a network, for instance, that has 50 hidden layers in it, and that's not even the most complicated use case that we'll cover. But if you can come away understanding that sieve analogy, then there are just a few more things to kind of keep in mind to make sure that that the rest of the presentation isn't like totally confusing to you. First, let's remember that the goal of training a neural network is really to reduce this cost, or this distance that these hidden layers containing these retained and randomly generated weights, generating output matching the labeled training data. So when we randomly throw stuff in, what gets us closer to what we know the right answer is? Let's retain what gets us closer. Let's throw away what doesn't. By doing that, we reduce what's called the cost, and we use these crazy statistical mechanisms, things like we use cost optimization algorithms, statistical cost optimization algorithms, to try to determine the best cost. That's all part of what what goes into doing the training of a neural network. But again, it's all about let's put random data in, let's see how close we get to our known output, and then let's retain what got us closer in those hidden layers, and repeat what works and throw away what doesn't work, and do that hundreds and hundreds of thousands of times until we have a series of weights and biases that gives us good predictions on our input. So we need to know that. And once we have that, we can transfer that to any number of learning platforms that we want to, and then we can just pass arbitrary input into it, stuff that we would actually want to use in real life to get our predictions based on. So again, maybe we've trained a set to recognize handwritten numbers, and we went through all that training, and now we actually want to use it. Well, that's what we do. We just would start passing in pictures of real world numbers that we wanted to do this analysis on, and we would start retaining our output. A lot of open source software frameworks exist, which can assist in creating and training these models. You really don't have to do very much from scratch anymore. Largely, with some of these libraries that are going to look like, you don't even really have to understand more than what I just kind of described in terms of understanding neural networks. You might want to become familiar with a few specific types of neural networks. You definitely want to learn a little bit more about things like gradient descent and cost optimization, and learning things like backpropagation and be familiar with how that works. But these frameworks really do a lot of this for you. You really don't end up writing a ton of code. Right now, the biggest challenge isn't really about creating these networks. It's about getting accurate labeled training data. Okay, so getting the right type of data to train these networks to actually work and be practical for us is the real challenge. And that's why you hear things nowadays like data is more valuable than gold, because companies like Google and Facebook, who can provide this training data, this labeled data to train robots effectively, can sell this stuff for billions and billions of dollars because they know that this is going to improve business efficiency by doing these menial tasks. So that's why this data is so valuable, because it's hard to come by a large enough and accurately labeled set of training data that can be used to properly and accurately train these networks in the first place. So if you can keep those things in mind, you should be good, and we can jump into some company stories. But I'm gonna stop there for just a minute, having just dumped all of that, and kind of turn to you, Eric, for a moment and say, how do you have any questions? Do you want me to drill down on anything more? How do you feel about what we just talked about?
No, I love it, and I love October basically saying, no, that sounded good. Now,
he's agreeing with most of what I say. He's got his own opinion.
I think so. I think he is agreeing. No, that was really good detail, and I like the fact that you broke down what all these hidden layers are about, and I love the sieve example. That's kind of how I've looked at it myself, where you're sort of shaking the sand, the little bits of data through different layers, and you're trying to kick the system enough to where it's random enough such that the algorithms can do their job and it can start finding the patterns. I was actually talking to a gentleman just yesterday who's done some really interesting work with simulation models, and he was saying exactly what you were saying, which is that you have to kind of, I don't want to say kick these things, but you have to shake them a little bit to get them off kilter, because otherwise you could wind up with that case of overfitting a model, for example. Do you want to maybe just very quickly describe what that means to overfit a model and explain why randomness helps to avoid that?
Oh, yeah, sure. So one of the biggest challenges to training a data set is this problem of bias. And bias is you have to think about it in a couple of different ways, right? There's mathematical bias, which is where we're applying another set of variables along with our weights to the data that pass through the hidden layer to add both retention and randomness to the math and the learning. But there's also this problem of bias in the real world. So the classic example is, if we has actually been looked at kind of along racial lines, which is interesting. We've had certain data sets that were where we tried to find things that would be, just little consumer level stuff like product placement and ad placement to certain demographics. Well, we found that what happens is when we gather the data, or even the team who gathers that data, if they're from a certain demographic, they're going to be drawn to providing data that matches their demographic. And those patterns, even though they might not be discernible to us, these networks are sensitive enough to allow that bias to improperly train, and then they only work according to the type of data that's been included in that training set. So when we say that something's been overfit or overtrained sometimes, what we mean is when we're training the model, what happens is this phenomena where you see the accuracy start to plateau and even possibly go down as you start feeding more and more random data into the system. It's like you'll start peaking, you're like, oh great, we're hitting 94, 95, 96% accuracy, and then all of a sudden, boom, we just stay there at 90. You keep trying to train it, or we start getting worse. And what's happened at that point is we've hit this threshold where we call what's called overfitting the model. At this point, the training data that we've used, there's too much conformity in that data to accurately give us predictable results out of real world random data. And so the fix then, interestingly, and there's very complicated math, which is above my head, honestly, in some areas, that can prove this out on a piece of graph paper and with a long series of symbols. But what happens is those details, that similarity, that conformity across the data, means that those very, very minute differences in weight and bias that get us training sets stop working when we apply them to something that doesn't fit within that data's conformity. And so if we throw the thing data that's already kind of disparate and weird and random, it's going to take a little longer to train it, but it's going to give the system the ability to explore, effectively to see more edge cases, more outliers in data, and you become a more accurate training set that way. I hope I did a good job of explaining that. It's a very oversimplified explanation of what's actually a very discrete and difficult math problem.
Yeah, no, this is really good stuff, because again, and I remind people, but artificial intelligence is not perfect. It is artificial after all. Machine learning can be very powerful, but you really do have to monitor the outputs, what it's telling you. And then, of course, in the real world of production, you want to have your challenger models running in the background. And when your production model starts to fade, as you mentioned, well, then you either tweak it or you bring in a challenger model. So the point is, it's always a work in progress. And what you want to watch out for is this concept of overfitting, where your own bias or, frankly, just not putting enough effort into it can lead to bad results, and you can lead to misleading predictions. And that's the whole idea that you want to avoid, right? So yeah, that was great. And I'd say go ahead.
Sweet. And in fact, we're going to see a couple of these very specific challenges in these use cases and kind of talk about how they were overcome. Airbnb ran into a classic version of this problem. So we'll dive into it. So, all right, well, let's just go right in. So again, there's a lot of companies now, enterprises that are benefiting from machine learning, and they're using it for lots of different things. And so it's challenging really to come up with a short list of companies that I thought were doing pretty cool stuff, because there's a lot of companies doing really cool stuff with machine learning. But I thought this would be a nice kind of range of use cases, just because we solve, I think, very different problems with each of these company stories, and there's some similarity in the technology stack, but it allows you to see sort of some different approaches to using this stuff. So actually, to introduce everything here, on the bottom we have Comma.ai. This is an autonomous driving platform with a really cool story, and we're going to save that one for last, actually. It's my favorite. I love all three of these, but the Comma.ai story is really cool, I think. We have Airbnb on the left. We're going to see how they solved kind of a textbook problem, but one that, because of Airbnb's scale, became very difficult to try to manage on their own without machine learning, as well as some problems that were overcome in MRI accuracy using machine learning framework that GE Healthcare developed. And in the middle here, we have this logo that's a T and an F, when you shine a light on it from either side. This is the TensorFlow logo for people who might not be familiar with it. TensorFlow is an open source deep learning framework that was created at Google. And two of these use cases are making use of TensorFlow. In fact, Two of these use cases for sure are making use of TensorFlow to assist in creating their learning models. So it was created originally at Google as part of their Google Brain project, and it's still in use in Google. If you look at what TensorFlow is really best at, they should bear some similarity to some problems that you see Google solving. So, for instance, Eric showed you the kind of predictive text. I don't remember the name of it either. Or the Smart Compose.
Smart Compose, yeah.
Smart Compose that the Gmail gives us now, the ability to finish sometimes entire sentences based on what we typed previously. TensorFlow is used to do that. There are types of neural networks that are used for lexical analysis or word analysis that can really, again, there's no magic. It's just a lot of math. What they can do, what these neural networks can do, is they can take a look at all the email you've ever sent in your life, ever, through Gmail. They can chop it up into tons of different representations of the way that you wrote those emails. They can feed them through neural networks, and then they can say, in the past, when you typed these things, there was a really good chance that you typed these other things next, right? That's all the algorithm is doing, is it's finding patterns in the emails that you've already written and saying, I'm just going to try to repeat this pattern. And as Eric pointed out, it's not always right. It was going for, Eric was going for today, and it wrote tomorrow. But where we're going, we're not there yet, but the way that we improve these last few bits of accuracy is really through just providing more computational power. Because if we had the ability to, say, have that network fed on Eric's calendar as well, and we were able to suss out that the calendar was tied to tied to an invite from someone who he has a meeting with today, then the network might have been able to pick up on the pattern with broader data to say, okay, well, not only could this be today or tomorrow, but hey, in cases in the past where Eric had meetings with this person during today, he typed today and not tomorrow, right? So that, again, maybe it wouldn't be solved exactly that way, but it's just a brute force pattern matching thing that looks like magic, and it really is powerful. But it's just brute force pattern recognition and pattern repetition. And TensorFlow is used in a lot of cases to produce this. So what it really does is simplify our models. It simplifies all of that mathematical work that we just talked about. Rather than having to go and try to do that stuff by hand, we have the ability to use APIs to create those objects and structures and training loops and feedback and propagation and all that stuff behind the scenes. We can just focus on designing the layers as developers and changing the structure of the networks and our activation functions and our cost optimization and all of that stuff. We don't have to worry about producing the code that's going to train and retrain and show us the output and everything like that. And it's got a bunch of very useful algorithms built in, a bunch of different types of neural networks already created for you out of the box. And programming really just centers first around defining a deep network and its layers and then training that model continuously. But all this stuff like backpropagation and cost optimization and feed forward and everything are handled for you modularly. So all you really need to do is think about the kind of neural network you want to build and the characteristic of the layers. And you can just play around with it. I mean, you may not know, coming into a machine learning problem, it is typical, I should even say, for ML developers to come in to a machine learning problem not really knowing the best structure, the best neural network structure to use for the problem that they're trying to solve. They may do many different structures before they center on one that actually works. In fact, Airbnb, which we'll look at in a second, did this. So what TensorFlow again lets us do is not have to think about all those components and program them by hand. We can just do them through a more of an API approach, which has empowered businesses really to get with machine learning and to be able to do very sophisticated AI and ML types of functions without a crazy AI ML skill set. I mean, TensorFlow really does make this stuff very approachable. So what is it that Airbnb was trying to solve? Well, they had this problem where, users or hosts, people who are hosting their properties, are going to be uploading photos into the site. And as we all know, Airbnb exploded, and there's tons of photos being uploaded. And Airbnb really didn't have a way, a reliable means of ensuring that when someone says this is a living room, this is a photo of a living room or a photo of a bedroom, that it really is a photo of a living room or a photo of a bedroom. They also ran into classic problems which we'll look at in a second, where people might hosts might mislabel the data, and they might say this is the view from the living room, and it's really a picture of like a window in somebody's backyard. But it gets classified as a living room picture because it has the term living room in it, right? So obviously doing that type of classification is not going to work at scale accurately for the millions and millions of user-provided pictures. So this is a problem that Airbnb had to solve. They knew that they wouldn't be able to solve it using just relying on host labeling, because that's prone to human error. They could pay a company to come through and label everything by hand. That's how we've dealt with some of these problems in the past. But at their scale, it would be very cost prohibitive to do that. And so they turned to machine learning to instead say, can we use deep neural networks to find patterns in these pictures that can help us decide if this is a picture of a living room or a picture of a bedroom or something like that. Now, the problem that they had here is kind of close for anybody who's looked at some of these more textbook or academic problems around machine learning, but not identical to image classification problems. Most of the image classification stuff that you see today is about object recognition, right? Again, going back to those CAPTCHAs. Is this a picture of a telephone pole? Is this a picture of a stop sign? And it's no secret that, or it should be no secret anyway, that so many of those are pictures taken from Google Street View, and we're asked to do them on CAPTCHAs. Why are we doing that? Because we're trying to train models that are going to work for self-driving cars. All right. When you really start looking at the data classification that you're doing by hand when you do CAPTCHA work, for instance, and you start thinking about the broader concepts of training robots, you'll start piecing those things together. So when you sit there and do that CAPTCHA, it's annoying, but you're helping in your own small way to get us to self-driving cars. So maybe think about it that way instead of, oh, this is annoying and it's wasting my time. But anyway, this problem was not about object recognition. It was about classifying the picture itself. It was about saying, okay, I don't care if there's a coffee table in this picture. I really care about if this is a picture of a living room. And so they modified an existing deep neural network called a residual network. This is a type of deep neural network called a residual network, and it's there was already a published trained model provided by a company called ImageNet, which is publicly available, called ResNet. So in this case, and you can go, anybody who wants to can go and use ResNet. It's actually provided as a type of neural network by some of these libraries like TensorFlow or Keras that we're going to look at in a moment. And so it was close to what they needed, but not exactly what they needed. Again, it wasn't about recognizing images or objects in the images. It was really more about, do all these objects in this image constitute a living room or a pool or a kitchen? And so they altered just kind of the top two layers of that network. It was surprisingly easy to alter the ResNet published network to really just add a couple layers at the top that would go with with two sets of trained of training data. One was this golden set that they actually did pay a third party to generate, maybe looked at 30,000 some odd images and labeled them, that they knew were accurate and that they paid somebody to do. And then they paired that with their kind of poor data or untrusted data that they got from their hosts or users. And you can see right here why this could be considered wrong. This is all some of the bad data that they had to deal with. So for instance, the host said this is a picture of the stairway up to the bedroom and the kitchen, but their earlier labeling algorithm based on just lexical analysis would say, oh, okay, so this is a picture of the kitchen, but obviously that's not the kitchen. Or here, the view from the bedroom, but well, okay, this is definitely not a bedroom, but this is what the labeling algorithm labeled it as before. So they needed to do a little bit of filtering here. Removing words like entrance or whatnot. But then they were able to scale against this user-provided training data. So now we've got millions of pictures that are relatively useful, but we can test that data against golden set data that we actually paid for that we know is 100% accurate. So it was kind of an interesting approach, but it worked very well for them, and then created a scalable system where they can control the cost of the third party doing the actual labeling of the data while relying on their vast host network to provide the actual training data not used for testing. So interesting approach. We also needed a lot of computational power to pull this off. Right? There are millions of pictures, user-submitted pictures being processed, and TensorFlow really helped here because it very easily can assign training tasks to GPU threads. It's just built to be able to do that. You want to run train your network on one GPU thread. You want to train it on 8. Very easy in the way that you deploy to set that affinity of what GPUs are allowed to execute the threads. In this case, 8 separate GPUs across Amazon EC2 XLarge instances. And with this, according to the dev team, the most accurate model was obtained after training this pre-weighted rated data over what we would call 3 epochs or sets of training data that we're passing through, lasting a total of 6 hours. And the accuracy varied a little bit. And interestingly, some of the patterns were easier to recognize in certain types of rooms, like so bedrooms ended up being like 3% easier to classify than a living room. Some of that, is interestingly around the variance. So there's a little bit of a paradox in that on the one hand, living rooms tend to be a lot more random. You have coffee tables, maybe, or maybe not a coffee table. Maybe somebody has an ottoman instead. Maybe they got a TV. Maybe they don't have a TV. Maybe there are, conversation pieces on shelves. Maybe there aren't. Maybe there's posters on walls. Who knows, right? So living rooms tend to look a lot different than bedrooms. So the training data is actually a lot better because the data is a lot more random, but we just don't have enough of it. So we, in the long run, probably could make living room detection more accurate than bedroom detection with a much larger data set. So there's that paradox, that overfitting paradox kind of in action right there. So the production implementation then, when we actually got this thing working, allows Airbnb to do like virtual tours. So, when a host signs up at Airbnb, they don't actually say like, hey, these are all pictures of my living room necessarily, and they make a tour for you that's just pictures of their living room. There's now an algorithm run by TensorFlow that's doing that categorization and then creating the virtual tours for you group by a room. The feedback and training data is very scalable, given that it's this nice hybrid solution of using this golden set as well as the user-provided image data. TensorFlow, again, made it very easy to make this whole solution scalable, and really with not a huge amount of development because it was really just a modified ResNet 50 deep neural network that they used. And some accidental innovations came out of this as well. So for instance, they did find that there was some usefulness around object detection in images, which let them sort of rate the quality based on the kind of amenities that might be included within those rooms. So if it could detect, that it had nice large French doors, for instance, then, that might be listed as an amenity. It was also easily kind of accidentally discovered that we could use these models to classify images as being indoor or outdoor using unsupervised training, which was interesting as well. The ResNet 50 was good enough and well-trained enough without supervisional data to be able to determine at least whether the picture was taken indoors or outdoors. So that was pretty interesting. But at the end of the day, again, trying to do this classification by hand or relying just on user supply data would be pretty much impossible, or at least wildly inaccurate, given the way that the free-form nature of the labeling from the hosts, or how expensive it would be to hire a third party to do all this labeling by hand. TensorFlow and deep neurals, it then was actually cheap and repeatable for them. All right, so that's the Airbnb use case. Thoughts on that one, Eric? And also, I realize that we're down to only about 15 more minutes. I've got 2 more use cases to talk through.
Keep going. This is great stuff. I love the detail that you're giving here, and I like the line where you said just trying to do this manually or with user-provided data would be wildly inaccurate. I mean, what you're kind of pointing out is that you really do want to use the machines whenever and wherever possible, and be realistic about what to expect, right? So this is great stuff. Go ahead.
Awesome, thank you. Cool. So let's talk about GE Healthcare and what they've done. So where was their challenge? Well, people's bodies are different. Right? And MRIs are actually very sophisticated machines where techs need to know how to point what's called the right plane when they're sort of slicing through a part of a person's body and trying to, not really slicing, but using magnets to do it, to get a picture of that part of their body. So without giving you a medical degree, part of being a good MRI tech is being able to take a look at these, what are called localizer images, these first kind of low resolution images that are taken of the body, and then determine based on those images what anchors the MRI should use to slice the desired part of the anatomy that we want to look at. All right, so it's a human process of an MRI tech saying, okay, I think based on how these localizer images look, I should feed these coordinates in, and we should scan this part of the body and hopefully get what the doctor is looking for. But it's prone to human error, and really it's based on the skill set of the tech. A really good MRI tech is going to be better at lining up and pulling the data than somebody who isn't as well trained. And the failed operation can be costly to the hospital. It can mean having to retake the images. It can mean sometimes, in pretty extreme cases, can result in misdiagnosis or looking at the wrong part, the anatomy. I mean, it can have, consequences. And of course, this becomes even more compounded when we're scanning very complex areas of the body, such as the human brain. So here we are actually using artificial neural networks to scan real neural networks, which I think is kind of cool. We needed a way to automate then the process of determining where these scans should take place based on these localizer images without a human in the loop. And so to do this, we just trained on these localizer images that had already been captured to look at very specific landmarks in the brain. So again, it's not perfect. This says if you're trying to look at this part of the brain, which I'm not even going to try to pull out a part of the brain, I'm definitely not a neurosurgeon, but if we're trying to look at this one part of the brain, here's what the localizers should do, right? So very commonly looked at landmarks in the brain is what we trained, is what this trained against. With a train set, then, these localizer images could be input, and then the neural network can report on how useful those images are going to be for targeting the landmark. Okay, so the algorithm isn't necessarily, at least at its first pass, saying, here's where you should set the machine. The first thing it does is actually just say, hey, these localizer images that you just took are either really good or they're really bad. You should retake them. But when the tech gets that negative feedback and the tech learns, oh, that's a bad image, that saves a ton of time because they can just take the localizer image again and not have to do the entire scan, find out that it was a bad scan, have the doctor come back and say it was a bad scan, have the patient come back in to repeat the scan. Instead, they can just learn immediately. It's almost like shifting left, if you will. We can learn in development that we have a problem with the localizer image before doing the final scan. And so to achieve this, GE used TensorFlow with an interface called Keras, which created these 2D and 3D, what we call cascading neural networks, which are a type of neural network that's really good for medical image analysis. And so Keras makes TensorFlow even easier. And for anybody who's really just getting into this stuff, you probably can jump right into TensorFlow, but you'll have a much better time if you start with Keras, because you're going to be able to experiment very easily on day one with a lot of different types of neural networks in a very API-driven way. Your code will just say, hey, give me a 2D convolutional neural network, and it'll just give you one, right? So it's very, very so I definitely recommend starting with Keras. And GE did that to kind of springboard. And just to give you an idea of how easy this code is, if I want to add a hidden layer to an existing model, I can do that with one line of code. So you can see me doing here, I want a dense layer using what we would call softmax activation function in our neuron. I want it to be of size 32, so it's like a 32 by 32 matrix. And I want to add it to my model. And then I want to add another layer after that. But this one, I want to use sigmoid activation, a different type of activation function, which is good at finding different patterns with a different size and shape, a different sieve, right? So these are two differently shaped sieves, but I'm adding them to my model in one line of code using Keras. So it's very easy. And then once my model is built, I run one line of TensorFlow to actually tell TensorFlow to start training that model once it's been told how to get input. So really can start very quickly on complicated machine learning problems by using this framework. In the end, GE's process was kind of three basic mechanisms that these neurals were performing. The first was quality analysis. So again, are these localizer images even good? Then it would provide this readout to the tech saying, hey, these localizer images are so good that these are all the different landmarks of the brain that you'd be able to accurately visualize based on those localizer images. And then finally, we can provide details to the tech, the actual planes to scan. I'm going to pause for just a second. At this point, I'm going to let the cat in the office here. He's scratching.
The cat's out of the bag now. No, this is great detail. Go ahead.
So anyway, so he's going to be joining us, and he'll quiet down now that I've let him in. For all three of these steps, built-in features of TensorFlow were able to assist in providing all three of these things. And with their current trained model, the whole process is able to evaluate based on those. It's able to evaluate those three things based on the localizer data in about 3.5 seconds on a decently powered machine. So very easy for techs to be able to perform inside the clinics. We got varied images used, and collected actually only a total of 29,000 images, but we're still able to achieve 99.2% accuracy. Now, a lot of that's due to the fact that MRI data is very, well, it just doesn't vary very much. It's got the same colors, it uses the same dyes, the structures are very similar. So it was actually not too hard to train this one. And now it's a trademark product that goes under the AIRX product name, and cuts the time that's actually needed to perform an MRI scan nearly in half, while also providing a great deal of accuracy. There's a lot of, they do a great blog on this actually. It's a really good read. And I'm not going to go through all of these in too much detail, but this is straight from their blog article. These are the reasons that the developers say that they chose TensorFlow to solve this problem for them. Number one being the support for just having 2D and 3D cascaded neural networks built in. That was the main thing for them, but there's all this other stuff too. Libraries that allowed them to do image manipulation, which made it easy for them to provide visual feedback right in the image to the text. Continuous development, graph computation, the Keras interface to make things easier, ease of deployment around TensorFlow. So anyway, really good reasons for them choosing TensorFlow here. And if you're interested in more detail, you can see this blog where they kind of go into detail about this whole development process. All right, last, certainly not least, and probably my favorite out of all of these is this kind of upstart company, Comma AI. This is not a TensorFlow example, actually. I'm sure that TensorFlow was used for some of the early modeling and stuff, but when you look at the code for Comma AI, it is very specific to what we're trying to do with this project. But the Comma AI company, their flagship product is completely open source. You can download it and use it today. Called OpenPilot, is a fully open source autonomous driving platform that's built on Python. Now, you may have read some blog articles about this, about the guy who can run his Acura from his iPhone, his hacked iPhone, and that's very true. The platform does run on an iPhone, or can run on an iPhone, I should say. But it was launched by somebody who's he's no lightweight, all right? A guy named George Hotz, who, if you're familiar with him in the hacking community at all, this guy has got a ton of street cred. He's the first person to successfully hack the iPhone. That's what really put him on the map. And now this is his current project. And it's very hackery and very cool, and potentially very disruptive. He was able to, using really nothing but a LiDAR mount, so laser radar mount, and roof-mounted cameras, successfully autopilot his Acura ILX using just this OpenPilot software, and then an interface that fed into the car's automated cruise control and steering and stuff like that, and power steering and everything. The source code is totally available here on the GitHub. It's released under the MIT license. There's a number of different open source components that it was built upon beyond just Python to create it. So libraries for mobile interfaces, communication between software and the vehicle. But again, the stack is the least impressive part of why this works, and why Hotz's project is so much different than the automation that we see coming out of like Tesla or Apple or Google. And it's the way that he trained the model. He really put a lot of faith into deep neural networks. So traditionally, what a lot of these other companies are doing right now as we try to get full autonomy is that we try to have the cameras or the software recognize an object like a stop sign or a traffic light or whatever, and then react to that object. Okay, but it's very imperative. It's very see this, do that, see this, do that. And a car can already be trained to do, recognize other cars and lane indicators and things. And so then it can accurately recognize situations and respond to those situations. The problem then, though, is that trying to account for all those scenarios is hard. How are we going to possibly think of everything? And that's really the hardest part then of taking this approach to doing it. So Hotz, being the hacker that he is and the disruptor that he is, just said, all right, let's totally rethink this. Instead of trying to recognize every possible driving situation and react to it, let's just use a deep neural network. Let's feed it hundreds and hundreds of hours of dash cam footage of real drivers, and then just tell it to repeat the behavior that it learned watching those videos. So instead of trying to train it like nitty gritty, giving every detail of the driving experience, he trained it using the way that most of us learned how to drive, which was watching somebody else drive. So I think it's really interesting. And the fact that it works, and actually works frighteningly well, right? So I think the pattern, these really amazing pattern recognition capabilities that these deep neural networks provide for us, and Hotz just had to have faith that it would work, and because it does. But it also, I think, really demonstrates that human ingenuity is always going to play a part here. There's so little to fear at this point, because if a computer never would have made this intellectual leap that Hotz did, never would have said, hey, you're training me wrong. This isn't the right way to design me. It took a human to say, oh, wait, there's such an easier way to do this. To really put this in perspective and how disruptive and why a lot of people are a little miffed about this, it cost Hotz $50,000 to build a completely self-driving car. $30,000 of that just went into the car itself. Right now, from Comma AI, you can purchase a dev kit version of this for $600 that allows you to run OpenPilot. Maybe 100 or so vehicles are all listed on the site. Usually newer models that allow control over cruise control and things like that. But 2018 and up are most of these models. So there's a lot of cars that you can just turn into a self-driving car right now for about $600, and then running the software. This is a picture of the original rig that he built. It was running on Ubuntu. This was his modified Acura. He also replaced the transmission with a joystick, which is kind of awesome. And engages the self-driving. And now here's the consumer edition that you can go and buy today. And then so the rig that you're buying, it's almost like buying a Raspberry Pi. It's just kind of a blank bit of hardware that allows an interface into your car. It's like a harness, really. And then you install the OpenPilot software on it. So it also leaves, it's an open hardware type of initiative too. It means what I love about George Hotz and the way that he approached this and the way that hackers approach things is that it doesn't just have to run OpenPilot, right? This is a nice universal interface into the parts of your car that are necessary to make it autonomous. And if you don't want to run OpenPilot on it, you don't have to. So I'm just going to close with kind of a few more thoughts on this. I know we're getting near the top of the hour, or I think we are at the top of the hour. Thanks for sticking with us. A few things really are clear here. I think that AI and ML are already very powerful forces in our lives. And they're becoming more powerful as we find new applications and better ways to train our data. Where we go from here is going to be supported by open source communities, and I think that's great. And the reason that I think that that's great is because when the code is open and transparent and we can all see what we're doing, then we don't have these fears of shadowy organizations creating machine learning projects that are going to destroy our lives, or, it's the shadowiness and the hidden stuff that we always have to fear. But when these projects, the leading projects, are being developed in the open by communities where we can all see what's being done, we can all breathe, I think, a sigh of relief, and really able to focus on the great things that we can accomplish and not the potential dystopian fears that some people have. But at the same time, it should be called out that today, only a handful of large corporations are going to have access to these data sets that are really necessary to train these models for the next generation problems that we're going to be solving. And an even smaller number of those companies are able to curate and grow those data sets, which they sell for astronomical amounts of money. And so really, although I'm so optimistic about what this is going to do for us, I think it is worth saying that as software professionals and enthusiasts, we do have a responsibility to understand this technology, to understand how it works, to contribute to its direction if we choose to, so that it isn't just a few companies with access to the data and access to the algorithms that really are going to define the landscape of the next decade and probably beyond. So that's most preachiness you'll hear from me. I will say, though, that if you'd like some assistance learning more about this stuff, this is what our company does. This is what OpenLogic does. We connect you with people who are leaders in the industry, leaders in open source, across a lot of different applications, and of course, machine learning is one of those. So if you're interested in reaching, in talking to some of us, please reach out and go to our website, openlogic.com. And that is the end of my preachiness and my sales pitch. I'll hand it back over to Eric. Thank you.
Yeah, no, this has been fantastic, Justin. Thanks for going into all that detail, folks. That was the end of our show. We burned through an hour. We do archive all these webinars for later viewing, but that is just a preview of things to come. I have to say, the folks at Perforce and OpenLogic, very talented, very smart, and have a lot of great technology and understanding of technology. And I think you're exactly right. They're moving us toward an open source future, and that's where we want to be. So with that, we're going to bid you farewell, folks. We'll catch up to you next time. Got a big event tomorrow with Microsoft. Don't miss that. All about success stories and analytics. We'll talk to you next time, folks. Take care. Bye-bye.